Mathematics usually starts with a map. We use a flat grid called the coordinate plane to plot out individual points and draw the shape of equations. On this map, the most crucial landmark is the horizontal x-axis. This line represents every single location where the vertical value, y, is exactly 0. Look at this graph showing a curved function. Whenever the curve hits that horizontal axis, we call that exact location a root. To find these intersection points algebraically, you don't even need to draw the picture. You simply set your equation to 0 and calculate the remaining values. Finding roots gives us perfectly precise coordinates. It tells us exactly where a function exists in static space. But watch how this curve interacts with the axis. At one point, it cuts straight through the line. At another, it touches the axis and immediately bounces back. The algebra actually dictates this behavior. Notice how the crossing point is driven by an odd exponent, like a 3. Where the exponent is even, like a 2, the graph gets rejected and turns around. We can use this crossing rule to hunt for missing roots. If we know the graph outputs a positive value up here and a negative value down here, the curve is physically trapped. It has to cross the 0 line somewhere in between. Because the line has to start above the axis and finish below it, the number of crossings is always odd. It might cut through once or weave through 3 times, but it eventually reaches the other side. We now have an effective system for finding exact locations, but bracketing and roots are completely static. They leave us blind to how the graph actually moves as it travels between those anchor points. To measure that movement, we have to stop looking at isolated locations. We need to connect 2 distinct points with a straight line. By building a right triangle, we divide the vertical change, the rise, by the horizontal change, or the run. The sign tells us direction. Positive climbs right, negative falls, and 0 is completely flat. Finally, the number determines steepness, tying slope directly to the geometric angle. By dividing rise by run, we take a physical angle and turn it into a single algebraic ratio we can compute. Once we know that slope, we can lock it to a static starting point on the y-axis. That combination gives us y equals mx+b, the master equation for any straight line. This ratio dictates how different lines interact. If 2 lines share the exact same slope, their angles match perfectly, and they run parallel forever. If you take a slope, flip the fraction, and reverse the sign, you get a perpendicular line. Those 2 paths will always intersect at an exact right angle. But this entire system rests on one rigid condition: the angle never changes. If you try to use y equals mx+b on a constantly shifting curve, the math falls apart. Look at this roller coaster's trajectory. The steepness doesn't stay constant for even a fraction of a second. Every microscopic inch has a different angle. To measure a curve, we pick 2 widely separated points and run a straight secant line right through them. We slide the second point down the curve, shrinking the horizontal gap and adjusting the angle until the distance hits 0 and the points merge perfectly. We took the math of straight lines, collapsed the distance to 0, and forced it to measure a single instantaneous moment on a curve. This limit state gives us a new formula. This is the derivative. It calculates exactly how that slope behaves as the distance between points shrinks to absolute 0. Think about this progression. We started with roots, locating exactly where a graph intersects the ground. Then we built the concept of slope, measuring the constant steepness of straight lines. The derivative bridges those ideas. It gives us the exact steepness of a shifting curve at any single point. And that is the mechanism that carries us out of algebra and directly into calculus.